This video covers the properties of suitable raw material for my direct granules extruder and the specific implications for 3D printing. For the print tests I'm using version 7.2, the only difference from the previous version is a 1mm wide slot cut into the top section of the threaded sleeve over a length of 15mm. This slot is covered by the water cooling system, leaving a groove that acts as radial brake, thereby improving extrusion. The surface of the upper section is roughened, a feature that has proven advantageous in practice, given that the extruder tube is simply clamped to the water cooling aluminum block using 2 screws. The auger still is a standard wood screw with a thread diameter of 6mm and a core diameter of 3.7mm. With a 7mm bore, this leaves a maximum gap of 1.65mm between the extruder wall and the screw core. Consequently, the raw material used for printing must have a particle size smaller than this. So far I have worked primarily with recycled powder obtained from old prints. A modified grain mill is used to process the plastic waste, shredding the pieces with a high-speed rotating blade. Only particles that do not exceed the maximum size determined by the diameter of the holes in the steel plate pass through the sieve in the wall. Later in this video I will print with 2 additional materials, one I purchased and another one that was provided to me. Let's take a closer look at these materials. Shown here is industrial granulate. With a size of 3 to 5mm it does not fit into my extruder and therefore cannot be printed directly. The granules have an irregular shape without sharp corners or edges. They are produced by forcing molten plastic through a perforated disc and slicing it off with a sharp blade directly behind the disc while the material has not yet fully solidified. The sharp cut edge flows back together before the plastic solidifies, resulting in the lens-like particles seen here. The pellets are cylindrical with a diameter of 1.5mm and a length of up to 2mm. These are produced by chopping 1.5mm filament while it is cold. Consequently, the cut surface has sharp edges. Next we see the industrial PLA powder specified with a particle size of 400 micrometers or 0.4mm. It consists of very small, sharp-edged, irregularly shaped particles, indicating that the material was produced by mechanically grinding down larger particles. The particle size is not uniform. Many grains are visible that are significantly smaller than the specified 400 micrometers. After grinding, this material is also sieved and the specified size refers to the mesh size of the sieve used. The particles are transparent, no colorants were added to the PLA. The recycled plastic raw material I produced resembles the industrial powder, as it was made using the same principles. Mechanical grinding followed by sieving. This is an old batch I produced over a year ago, now I use a slightly finer sieve. The sieve had 1.6mm holes, resulting in a mixture containing noticeably larger grains compared to the industrial powder. The grains are also more colorful as I ground up material with various colorations. The raw material consists of solid plastic particles with air gaps between them, so what are the densities of the materials shown here? 100 cubic centimeters of granules weighed 69 grams, corresponding to an average density of 0.69 grams per cubic centimeter. For pellets it is 0.66 gram per cubic centimeter. For the recycled powder we get 0.55 grams per cubic centimeter. And finally for the industrial powder it is 0.51 grams per cubic centimeter. The density of the material depends on the particle size distribution within the powder. The box holding the pellets contains relatively large air-filled voids. These voids can be filled with finer material by adding powder that trickles into them. With the fill level remaining the same, the container is now 6 grams heavier. The average density is consequently 0.72 grams per cubic centimeter, representing the highest value in the series of measurements. Theoretically, the more densely the raw material is packed, the greater the amount of liquid plastic extruded per screw revolution. To what extent can the materials be compacted? To answer this question, I fill the materials into a 20mm syringe and apply light hammer taps to the piston. The granules show only a slight change in volume, which is certainly partly due to the deformation of the syringe itself. After compaction, the granules pour out of the syringe without difficulty. The same applies to the pellets. With the recycled powder, the volume decreases by approximately 1.5 ml. The powder cannot be easily emptied out afterwards. The grains have interlocked and friction against the container walls prevents the material from flowing out. The powder only falls out after light tapping. With the industrial powder, the piston sinks in by just over 2 ml. And here too, the material does not simply pour out. The mixture of pellets and industrial powder shows a volume change of 1.5 ml. If more powder is mixed in, the blend becomes more compressible. The properties of the powder dominate those of the pellets. Particle size distribution is a key property of powders, and not just regarding compressibility and flowability. Obviously, the powders can be mechanically pre-compacted within the extruder before reaching the melting zone. In the cold end of Extruder 7.2, this is achieved through the beveled upper edge and the stepped bore. Another property of the powders to consider during material transport to the extruder is the effect of vibrations. Here I have filled a glass with a mixture of the industrial powder and the green pellets. Now the glass is shaken for a few seconds, simulating the movement of the printhead and its hopper. You can see the large green pellets moving to the top, while the powder migrates to the bottom of the glass. The fill level is no longer uniform, and since the material intake into the extruder depends on it, this separation of the raw material must be prevented. In the printer I use, there's one stirrer attached directly on the screw axis and a second one in the front hopper. The two stirrers operate like gears, thus both are driven by the extruder motor. Printing fine details requires precise material metering. For this purpose, a small diameter extruder is better suited than a large diameter one. In my extruder with a 7mm inner diameter and a screw with a 3.7mm core diameter, there is a cross-sectional area of 28 square millimeters through which the plastic is forced. With a screw pitch of 2.8mm, a volume of 78 cubic millimeters is displaced per screw revolution. Extruders designed for industrial granules must be larger and consequently convey more material per revolution, albeit with a disadvantage of poorer metering precision. However, this calculated volume can only be extruded if the extruder barrel is completely filled with plastic, a condition that, as previously demonstrated, is not met with the four raw materials in their cold state. Here I have loaded the materials into a syringe with an inner diameter of 4.5mm. Looking at the sections of the tube, it is clearly evident that the degree of plastic infill varies. While the fluctuations in fill level are smaller for the pellets, it is still clearly visible that random voids have formed within the tube. Fluctuations are even less visible in the tube containing the recycled powder. With the industrial powder, this effect is even more apparent, precisely because it is virtually invisible. The smaller the particles relative to the extruder, the smaller these statistical fluctuations become. For the next experiment I actuate the syringe piston with a stepper motor via a rack and pinion. The granules are slowly forced out of the syringe to the left. The movement of the particles is not uniform. It can be seen that the granules occasionally snag on the tube wall, causing the grains to be forced more tightly against one another. When the tension is released, a wave travels through the tube and the grains redistribute somewhat more loosely within the available volume. Consequently, if the granules are lined up like beads on a string and set in motion, the material exhibits noticeably density fluctuations during extrusion. This effect can also be observed with pellets. The sharp edges at the ends of the pellets cause the material to choke on itself and the tube walls, resulting in a more pronounced wave motion than it is the case with the granules. The recycled powder consists entirely of sharp-edged grains, however these are smaller. Consequently, if a single grain snags, it does not block the entire tube. As demonstrated, the powder is compressible, allowing a snagged grain to shift inward and immediately break free from the wall. The material moves through the tube much more uniformly. Material transport is smoothest with industrial powder, it effectively flows through the tube. Entry into the extruder also involves fewer statistical fluctuations when the material grains are smaller. If only a single pellet fits between the screw and the extruder wall, it is crucial whether the screw can grip it immediately or if it first travels a few millimeters along the top edge of the tube. With powder, the movement of an individual grain is less significant. Statistical fluctuations during material entry are therefore lower. But why do granules or pellets exist if powder is so much better? Well, so far we have only considered the processes inside the extruder, not the material feed to the extruder. Granules and pellets are optimized for transporting material to the extruder. They have excellent flowability, meaning they can easily be fed from storage containers through hoppers and tubes. The sharp-edged powder grains exhibit higher friction, both with each other and against the walls of the feed system. Another downside of powder is its fine, dust-like component, which sticks to objects via electrostatic forces and is easily picked up by the slightest blast. Plastic granules are often coated to reduce abrasion during transport and so dust formation. In the experiment, the granules and pellets float downward without issue, whereas the powders clog the hose. The pellets also tumble out easily when emptying the printer's hopper. It is significantly more difficult to completely remove the powder when switching materials. I mentioned that the particle size relative to the extruder size determines the statistical fluctuations in material feed. If the extruder is large, the pellets are relatively small and fluctuations in the extrusion rate have less impact at higher volumetric throughputs. Extruders that use pellets as raw material are designed for printing large structures, not fine details. So, what kind of print results can be achieved with the materials in my Extruder 7.2? First I loaded the pellets into the hopper. Extrusion works in principle, but it is anything but uniform. In addition to the aforementioned pellet size relative to the extruder volume, another material property is responsible for the poor print quality. To print with the pellets I had to increase the filament factor, which determines the amount of plastic extruded per screw rotation, to 3 times the value used for the recycled powder. A reduction was to be expected due to the difference in density. Obviously the pellets are moved by the extruder with a very high degree of slippage. The smooth surface of the pellets, which ensure good flowability, cause the material to rotate along with the screw, as the extruder wall provides insufficient radial resistance to hold it in place. This also makes entering the extruder more difficult. Gaps visible on the walls of the track link indicate significant under-extrusion. In other areas, clearly protruding layers show that over-extrusion has occurred. I eventually addressed these pellet printing issues in a later video with a revised extruder design. Let's move on to the recycled PLA I produced myself. The printing temperature is set to 215 degrees Celsius, a 0.5mm nozzle is installed, the layer height is set to 0.2mm and the extrusion width is 0.5mm. The print speed is set to 30mm per second with an acceleration of 500mm per square second for the outer walls. I have demonstrated this test print using recycled PLA several times. The printed object clearly demonstrates, via straight walls and edges, how uniformly the material is extruded. The result is good, though some layers protrude slightly, indicating minor fluctuations in extrusion. Now let's look at the industrial powder. It is printed using the same parameters, with the only change being the filament factor. This had to be set to 140% relative to the recycled powder. Based on the difference in density, a value of only 108% would have been expected. Obviously the distinct flow behavior of the very fine grains makes the difference. The gap between the screw and the extruder wall is necessary to allow the air trapped in the powder to escape upwards. If this gap is too wide and the material being processed is very fine grained, slippage occurs between the screw and the extruder wall as the powder is pressed down. A smaller gap should ensure better powder feed. However, the slippage does not vary while the material is being fed to the nozzle. We saw in the previous experiment that the fine powder was forced through the tube very uniformly. Consequently, the extrusion process can be controlled very effectively, yielding the best print result of the entire test series. The transparent PLA shows no gaps, neither on the outer walls nor in the internal structures, and contains only a few tiny air bubbles. Encouraged by this excellent print result, I halved the layer height to 0.1mm for the next test, keeping all other parameters identical. The extruder now has to precisely dispense even smaller volumes of molten plastic. This works very well too. In a later video I will take a closer look, quite literally, at the challenges involved in printing very small structures. Before I can do that I need to upgrade both the Prusa printer and my camera equipment. I will also upgrade my powder mills to obtain better raw material for the prints. After all, I demonstrated in this video that finer is better. There is still plenty to do, so a big thank you to everyone who has supported this project financially and continues to do so, whether via Patreon or the donation button on my pages. A huge thank you to my anonymous major sponsor. Thanks for watching and I'll be back.